Hello, I'm Dan Gauthier, and I will be telling you about reservoir computing with autonomous Boolean networks on field programmable gate arrays. My collaborators are a former graduate student, Daniel Canaday, current graduate student, Aaron Griffith, and current postdoc, Wenson Barbosa, and we're with the Ohio State University. I've also had many senior collaborators over the years, including scientists at companies and at other institutions around the world, former postdocs, and former graduate students that worked with my group when I used to be at Duke University. And I'd like to thank the organizers of this second symposium on machine learning and dynamical systems for me to give a chance to tell you about our recent work. These projects were originally funded by the U.S. Army Research Office and then the Defense Sciences Office with DARPA, and is currently funded by Raytheon BBN Technologies. And this little figure here in the middle shows how we can instantiate networks for different information processing tasks on a device that's called a Field Programmable Gate Array that I'll be telling you about more in the next few slides. These are commercially available chips that you can purchase a demonstration board. And I have one example here of a recent one that we've been working with. You can see that the main chip is here. And this board in today's dollars, US dollars, is about $130. It's a very inexpensive way to get into doing experiments with complex networks. Before I begin, I would like to point out one of my former PhD students, David Rosen, who also was co-supervised by Eckhard Scholl in the Technical University of Berlin. David was the one that really developed the whole field of autonomous Boolean networks using these field programmable gate arrays. And his thesis was recognized as an outstanding thesis and published in the Springer thesis series, and you can even purchase it on Amazon. So I'll be telling you a little bit about these field programmable gate arrays, and then I'll take a little bit of an aside and tell you about one possible application of how you can realize neuronal-like networks. And there's a lot of interest in information processing using spiking networks, and it turns out with these field programmable gate arrays you can realize these spiking-like networks. I'll then move on to the core of the presentation of introducing the concept of reservoir computing. And then I'll tell you about how we go about forecasting a complex chaotic dynamical system using reservoir computers based on these field programmable gate arrays. And I'll give you a specific example of forecasting the dynamics of the chaotic Mackey-Glass dynamical system. And then I'll move on to the final topic of the presentation of controlling dynamical systems using reservoir computers. So these field programmable gate arrays are a commercial device where you can create almost any network that you would like. The idea is that a complex network has nodes that are represented by the dots in this figure, connected together by links through some possibly complex topology. And you can realize very large networks on these devices. It only takes a few minutes to reconfigure the network, so it's a very nice platform where you can really study lots of different variations, let's say topology or types of networks that you'd like to study. So these field programmable gate arrays are very useful for doing cognitive computing. The way that you actually tell the chip how to configure itself into one of these networks is using what's called a hardware description language, or HDL. There are two common languages. One of the early ones is called VHDL, and more recently most people adopt what's called the Verilog language for telling it how the chip to configure itself. So these logic elements that are on the chip are what we use as our nodes for a complex network. And a user can specify the logic function of these logic elements that are on the chip. The programmable nature of a field programmable gate array means that you have lots of these programmable elements, and the hardware description language tells the chip how those logic elements are supposed to behave. And you can then say how to wire it. So there's a complex fabric of wires with switches that can open and close. And so the hardware description language tells the chip which node should be connected to the others. And this has all the features of a true experimental platform. There is electronic noise, mainly charge noise or thermal fluctuations. And there's also slight manufacturing differences across the chip. So there's a little bit of heterogeneity that is built into the whole system. Now what's nice is that it's pretty simple to come up with a mathematical model that describes the complex network on one of these chips. And the other nice thing that about these field programmable gate arrays is that they match with existing computing infrastructure. So there's no need for going out and building a custom chip. You just take one of these commercial devices, and in many of the current chips, a section of the chip is actually a hard-coded central processor unit, a standard computer, and you can have very high-speed connections between the FPGA itself and then usually a Linux-based microcontroller that's right on the same chip. So it's easy to transfer information to a regular desktop computer or to send it over the Ethernet. Very easy to work with. So the way that we realize networks on an FPGA is we need to realize the nodes of a network. And as I mentioned, these are made up of what are called logic elements. And I can also collect these logic elements to make a super node of the system that has greater functionality. And I'll touch on that in the first example. And so these logic elements, you can program them to perform any logic type operation such as AND or XOR. And the idea is that I have n inputs, and n can be pretty much arbitrarily large, that are then sent into one of these logic elements. And the actual logic function for one of these logic elements is defined through what's called a lookup table or a LUT. And this lookup table or logic element sends out one output, but you can fan that out to many other logic elements or nodes in the array. Now, if I look in detail at the very high speeds, that these lookup tables take about 200 picoseconds to process a change on the input to give rise to a change in the output. So that gives kind of the upper time scale for how fast these logic elements can behave. But this time scale is incredibly fast in comparison to many other experimental systems that people work with. Now, in many cases, probably 99% of the users of field programmable gate arrays use these as true logic functions that would be used to create a special purpose processor unit for just accelerating code. And in that case, you apply a clock to the lookup table. So there is a central clock that is available on the chip, and you can wire that to each one of the logic elements. And the idea is that the lookup table only processes information that is presented to its n inputs every time there's, let's say, a rising edge on the clock. And in that case, we can treat this lookup table as performing an ideal Boolean function, and it just works like a standard type of computer. But in the vast majority of our research, we do not connect the clock. And if you don't connect the clock, then these lookup tables or logic elements behave as a highly nonlinear input-output device that has this time scale of around 200 picoseconds. So then I can really think of this as an autonomous logic element that can be used as the basis for trying to create an autonomous complex network. Now, if we want to connect together logic elements, as I mentioned, there are just wires on the chip that you can connect one logic element to another. But there are some cases that I'll be telling you about later, or we'd like to slow down the signal as it propagates along the link. And the way that we do that is that we purposely add logic elements along the links. You can think of this as making a transmission line that has a finite propagation delay through the system. So in typical cases, we will take one lookup table that performs the not function and then follow it by a second logic gate that also performs the not function. So having two not functions in a row just ends up being a copy of the input to the first logic gate. But what's important is, if you remember, I said that each logic gate takes about 200 picoseconds in order to have its output respond to a change in the input. So the idea is that if I put two NOT gates in series with each other, that will give me about 400 picosecond delay in propagating through both of those. So now I can string together a group of n of these pairs of logic gates to give rather large delays along the links. And remember, there's some manufacturing variations, so when I'm saying a logic gate responds in about 200 picoseconds, that means a typical gate runs at 200 picoseconds. Some are a little bit slower, some are a little bit faster, and there's a little bit of heterogeneity around the chip. So you really can't think of this as just being an integer type of delay. Also, these delays depend on the history of the gate. So if the gate is seeing very rapid switching, its delay time is a little bit different in comparison to the situation where there's slower switching going in. So now I'd like to transition to a first application of realizing complex networks on one of these field programmable gate arrays. And this is making these neuronal networks that I mentioned earlier. What I would like to do is to realize a neuronal-like network on one of these field programmable gate arrays, and we want to capture at least some of the basic biology that occurs in these neurons. And the idea is that I'm going to take a collection of these logic gates, combine them together so that as a group or as a block, it behaves as a neuron. So we have two primary blocks. One is called a pulse generation block that produces a pulse that should be the same every time. And then we have another block that controls the refractory period of the neuron. So the idea is that if a pulse comes in to this first AND gate, it will then trigger the pulse generation block to send a pulse out the output of the fake neuron, and then that's fed into the refractory period that then sends a signal back to the AND gate that then shuts down the neuron from responding to any new inputs through some refractory time. And I refer you to David Rosen's book about this. So two of the basic biological characteristics of neuronal systems are that they are excitable systems. And so that means that if a spike comes in that's too small, the neuron doesn't produce a spike, but if it's above a threshold, then it will produce a spike. So here I'm illustrating the case where I have a subthreshold spike and the output really doesn't have much activity at all. But then if I have a pulse that is above the threshold, then the output generates a spike. Now this refractory time says that if I have two spikes that come close to each other, you won't generate a second spike, but if they're further apart, then you will. I have that illustrated here. So these two pulses come in a time that's less than the refractory period. I'm assuming there's been no spike for a while, so the first pulse generates a spike. but then the second one, because it's within the refractory time, really generates no activity. In this case here, though, if the second pulse comes a time that's longer than the refractory time, then we generate two spikes. So we have realized this experimentally, and one illustration of the uh, excitable nature as well as the refractory time is just to take the input and hold it constant and above the threshold. So this wouldn't be very biological, but it illustrates how this works. So the idea is that if the input is high, it's above the threshold and it should generate a spike, but then the refractory period comes in and shuts down the neuron for a while, so it won't generate a spike until the refractory time comes. So in this case here, the output is just a periodic sequence of pulses where the width is set by the pulse generation block, and that's about 2.5 nanoseconds in this case. And then we set the refractory time to about 10 nanoseconds. So we see a periodic pattern of pulses that's generated by this neuron. And please note this time scale is very, very fast. So we can essentially do neuronal type dynamics, but now on the nanosecond time scale. We have studied various properties of these neuronal networks. We can wire them in clusters if we like, so we can have one cluster that's highly connected and then weak connections between them. And when we go about doing this, we've observed cluster synchronization. We've observed ways that this is fallen apart, and you lose synchronization, or you only have synchronization within one cluster but not the others. So there's a whole range of behaviors that are possible to study, and this is described in greater detail in this Chaos article published in 2013. So now I'd like to move on to a discussion of the main core of this presentation on reservoir computing. So I've been working in this area for probably 10 to 12 years or so. It was Ingo Fischer that really got me excited about moving into this field and starting to study dynamics of reservoir computers realized on these field programmable gate arrays. And we've published a series of papers, the first one going back to about five years ago. And I encourage you to look at my group's website. We have all the manuscripts posted there and easy to download. So in reservoir computing, just in general terms, let's not worry about the field programmable gate arrays for now. I want to do information processing with a recurrent network, which is motivated by what we think is happening in the brain and lots of other biological systems. The idea is that I have a complex network that has recurrent connections between it. That's what's called the reservoir, that serves as a pool or a reservoir of nodes that are available for doing information processing. The idea is that I have serial data potentially coming in on many channels that are passed through an input layer that then fans out this information to the various nodes within the network. And then I read out each one of these nodes to form an output layer. And what is important for the reservoir computing is that these weights of the connections between the input layer and the reservoir and the recurrent connections within the reservoir are chosen at random, and they are then frozen. We don't try to adjust those. It's only the output layer weights that are adjusted to optimize this network for whatever task that we're asking it to perform. And this output layer is usually just a linear combination of the values of the nodes within the network, or perhaps we might square or put the value of each one of those nodes through some kind of sigmoidal type function. But in the end, even if I do some nonlinear processing, I only add those values in the output weight. That means that I just need to use a linear optimization package, usually least square type methods, and so it's incredibly fast to train. So we don't need to use any type of iterative methods or backpropagation that's usually used in deep learning network. And that means that we get away from problems of nonlinear optimization. There's something that's called gradient descent that's often used for doing that type of nonlinear optimization. And often that gradient tends to vanish as you train the network more and more, and that really slows down training of deep learning networks. But we completely avoid that problem in reservoir computing in that we only have this linear optimization and there's no vanishing gradient problem. So these are very, very nice from the point of view of doing something where you need to rapidly update the information processing unit to take into account new data, or you want to train it on a completely new problem. It really just takes seconds to minutes of computer time for reasonable types of problems. So the mathematical description I'd like to use for a reservoir computer is shown here. Each node within the reservoir has its own dynamics. That is, it's described by some exponential decay or decay rate. I'm calling gamma sum I here. Each node could have its own decay rate. And then there's some nonlinear input-output function, Fi, that describes what the operation of each node within the network performs. So I have the possibility of connections coming in from the input layer. So the inputs I'm calling U sub j, and there are weights wij in that tell us how that information is fed into each one of the nodes. And then I have connections from the other nodes within the network each xn. And I specifically include the possibility that there are time delays for that information going from one node to another. And then there's a possibility of a bias that you might put inside this function. And then the output layer is often just taken as a sum of the states of the node. So although sometimes we do generalize this to perhaps being the square of the value of the nodes. Now, again, just to stress, these W in and W reservoir are chosen randomly at first. They're fixed and they're not trained. It's only W out that we train. And again, that's just a linear optimization problem. We typically use what's called supervised learning for training these reservoirs. The idea is that I have some set of data that I'm going to feed into the reservoir, and I'm going to record the output state. And I know in advance what that output should be for that particular training set. So that's what we're calling Y desired. It's the desired state that we know of in advance. And we collect a block of data coming out of the reservoir that's put into this matrix X, and then W out is just equal to these matrix multiplications and the inverse of a matrix. This parameter alpha is what's called a regression parameter or ridge regression parameter. It prevents us from overfitting the data, and this helps the network generalize to data that it hasn't seen in advance. And the symbol I here is just representing the identity matrix. So there are various fast algorithms that you can find in different languages like MATLAB or Python for doing this operation. And we typically use what's called ridge regression, but there are many other least square techniques that you can apply to the problem. And the idea is that once I do the training and I find W out, then I can plug W out into this reservoir and now use it for processing new information that the reservoir has never seen. One of the applications that I'll be talking about is to forecast a time series. So in this process of forecasting, we have two different phases. We have what's called a listening phase where we train these weights W out. So the idea is that I have some segment of data that I want to be able to forecast behavior of that system that generated that waveform into the future. But I first need to give it a chunk of data that I use for training. I feed that into the network. I then form this output function y on the output layer. And the goal of this training is just to make y of t equal to u of t for this training period. Now, after I now have set those weights of the output, I then take the output of the reservoir and feed it back around to the input, and don't feed it any other data from the input. This gives me an autonomous dynamical system. Remember, the reservoir itself is a dynamical system. Now, by doing this feedback, I have an autonomous system that, if I do things right, should be able to predict into the future of what this time series should do. Now, I'd like to take just a little bit of a side just to give you a little bit of a teaser. What I've been doing in this introduction is telling you about these recurrent networks that we use for information processing. And Aaron Griffith, one of the current students in my group, did a very nice study of reservoirs, and he developed a technique to using Bayesian optimization to optimize the different parameters that are in the reservoir, what we call the metaparameters, that tend to improve the performance of the device. So some of these metaparameters might be the decay rate, or that delay time, or the spectral radius of the matrix that connects the nodes together within the matrix. And what he decided to do during this optimization procedure was to also treat the in degree of each node in the network as a parameter that needs to be optimized. So the in degree just tells you how many connections do you have coming into the node. And what he was surprised about is that the Bayesian optimizer kept driving the system to a case where the in degree was only 1. And so that has some very interesting consequences that I'm trying to illustrate here in the slide. So on the top left, I've got a cartoon of a standard recurrent network, and then this plot is half of what's called a violin diagram. It says if we go and choose a bunch of random recurrent networks, train them, and find out what's the error rate on the prediction task, how well does it predict into the future. This curve gives the probability of finding a particular error rate, epsilon, for each one of these networks. And so we find that there are some distributions. We have some networks that perform better than others. But then when he allowed the in degree to be a free parameter, what he found is that one way to have a network with an in degree of 1 is just to have a loop, and then he went and cut the loop. So this is what's called a delay line reservoir. So essentially you just have nodes that are on the line, and there's just dynamics of one feeding into the other, feeding into the other. So remember, each one of these nodes has a finite response time, and so this acts as a transmission line so that information fed into the beginning takes a while to propagate down the end. Now, what I'm not showing in either of these diagrams is the fact that we're still feeding information to each one of the nodes in this random fashion. So there's still the possibility that information that's propagating down the delay line will interfere with new data that's coming in. And what was so surprising about this is that when Aaron looked at many different delay line reservoirs where he just changed the random weights for the input, he also found a range of performance, and that the performance of these delay line reservoirs really is only slightly worse on average than the full recurrent network. In fact, you can still find cases where this delay line reservoir will beat the typical recurrent network. So this stresses that even though much of the field of reservoir computing has been pushing hard on the idea that these recurrent networks are crucial for information processing, Aaron's study shows that this isn't the case, and that this will hopefully be an entry for us to really figure out why these recurrent networks behave the way they do, and that it's much easier to analyze these simple networks. And from a hardware perspective, we hypothesize it's going to be much easier to just build one of these delay line reservoirs. Okay, now I did my little aside to tell you about these delay line reservoirs. Now I'm coming back. I'm going to show how we do this forecasting task using an FPGA-based reservoir computer. So as I have already mentioned, that a reservoir computer is a dynamical system that has some decay rate and some kind of nonlinear function of its inputs from the input layer, as well as inputs from other nodes within the network. And the idea is that we're going to use one of these logic elements, or a collection of logic elements if I wanted to make a neuronal-like network. So the issue that we've got to grapple with is that this function, f sub I, has to be a Boolean function because we're working with logic elements on a field programmable gate array. But I stress that each one of the variables, even on this field programmable gate array, is a continuous variable, and that's because we're not clocking the system. So to drive that home, what I'm showing here is a case where we set up a complex network on one of these field programmable gate arrays. We're not clocking the logic elements, so they're really acting as highly nonlinear input-output devices. And we configured it so it would show very high dimensional chaos. And then we took one of those signals and sent it to a high-speed connector that's on the board, and then hooked that up to an oscilloscope so that we could really look at the analog voltage. And so what we see here is that you can have very complicated analog-like behavior that's being generated by these logic elements, and that you tend to see spikes. You really don't see anything that looks terribly Boolean-like. And that's because this chaotic behavior happened to push itself right up to the speed limit of these logic elements. So we're very sensitive to the input impedance, that is capacitance and inductance on the input of the logic gates, and it really turns this into a true analog system. And that gives us the possibility that these unclocked autonomous Boolean networks could potentially show computing beyond what we would think is possible by a Turing machine. Now, one of the properties that people believe is important for a reservoir is that it has to show fading memory. And the idea is that information that goes into a network rattles around in this recurrent system, and then eventually exits the network and goes to the output layer. And the idea of fading memory is that at least in the long term, I should see the same behavior no matter what the original state of the network was in before I started driving it. That is, if I drive it with a signal, there's going to be some transient behavior, but then eventually the network dynamics should be synchronized in a generalized sense, or entrained by the input driving signal, and then I'll see some particular type of output waveform. Now, if I were to go back and replay that, re-enter the same time series, but start the network off in a different state, I'm going to have some different transient, but then it eventually should fall down onto or converge to the same entrained state as the first time. And that's what's referred to fading memory. And what we find is that it's important to match the time scale of that transient behavior to the dynamics of the signal that you're trying to forecast coming in. That is, we really should be able to match this decay rate for each one of the nodes, which is roughly related to the time scale for this fading memory, to the input signal. But the problem with these lookup tables, these logic elements that are on a field programmable gate array, is that we can't change the value of gamma. It's set by the impedance that's hardwired onto the chip. So we had to figure out some other tool at our disposal to change the time scale of the fading memory. And so what we realized is that adding delay along the links to each one of the nodes is a very effective way of changing the fading memory. So what I have is a plot here of the fading memory of the reservoir as a function of the mean time delay that we added along the links. In the case that I'm showing here, we have 100 nodes in the reservoir. We see that there's almost a linear dependence of the fading memory time scale on the mean link time delay. So now with that little bit of a background, where I'm now going to show you our results on doing high-speed forecasting using one of these field programmable gate arrays, and this work was published in Chaos in December of 2018. Now I've got to address a few other issues that come about when you're using an autonomous Boolean network for these reservoir computers. The data that is going to be processed is likely coming from a digitized version of some continuous real variable that might be observed. So likely I'm going to have an analog to digital converter on the front end that's taking some signal in from, let's say, a sensor. And these analog to digital converters have some clock that is regulating when they sample the input waveform. So I have some sample time delta t, but then the other problem is that I can't have a real number. These analog to digital converters discretize the real value and turn it into some number of bits. So the value that is generated by the analog to digital converter is going to be in some fixed point representation of the real value signal coming in. And for the work that I'm going to tell you about, we use 8 bits to represent the each input signal. And so what I now have is a set of 8 binary values, zeros or ones, that are going to be fed into the reservoir. So what's nice is that the analog to digital converter automatically hands us a binary representation of the data, which is great for then feeding into a Boolean-like autonomous network. And we're currently in the process of developing new methods to work with higher precision and without increasing the complexity of any of the logic they have to use in the autonomous Boolean network. And hopefully in a few months you'll be hearing about that. And now if we're to use this FPGA for making a forecaster, that is a reservoir computer for forecasting time series data, I have to realize that there are different parts of this reservoir. Some of them are clocked and some of them are autonomous. So this is really more accurately called a hybrid reservoir computer, where I have some clocked pieces and some autonomous. So it's the reservoir itself that I've been telling you about, where we have no clock. That's just an autonomous information processor with these highly nonlinear input-output devices that are the logic elements. But the input layer is going to be clocked because I'm assuming I've got data coming in from an analog to digital converter that has some clock rate, some sample time delta t. But then we also have to clock the output layer in that we end up applying the weights for the output layer using standard multipliers and adders. And so we need to also register the state of the reservoir also on a clock, which is synchronized with the input clock. So the idea is that I'm going to feed in a set of discrete sampled binary data coming into the reservoir. I'm going to feed in a block of training data, and then going to collect the data on the output layer, store that into memory, then take that block of data, figure out the output weights. And then once I have those output weights, I'm going to program them into the reservoir so that they're going to be fixed. And then I will take the output layer values and feed that back around to the input layer when I'm now trying to do the forecasting. And so then the reservoir becomes its own autonomous dynamical system, which should be representing whatever the input training data set was. And just to give you kind of a time scale, we're limited by the calculations that are done in the output layer to apply the output weights to the registered values of the nodes. And that takes about 6.25 nanoseconds. So that means that we can run this reservoir computer at a rate of 160 megahertz. That is, we can make a new forecast or a new prediction roughly every 6 nanoseconds. Now, the other issue is that we have these input weights and reservoir weights that are the connections within the reservoir. Those are drawn from some normal distribution. Usually they're real values. But the issue is that the function fi is going to be this Boolean-like function. So I don't want to slow down the system by having to perform these multiplications of wn times u and w reservoir times x, and then having this real bias there. But there's a trick that we play in that if I were to Booleanize u and x, then that means that we can perform this weight multiplication at the time that we synthesize the network, as we can do it in advance, assuming u and x are Boolean. And then this complicated expression just turns into a lookup table, saying that, again, we don't need to perform these multiplications over and over again in real time as the network is running. Just when we're figuring out how we're going to configure this network, we just assume u and x are Boolean multiplied by the wn's, and that gives us a lookup table that defines f. And what's wonderful is that these FPGA logic elements are based on lookup tables, as I said earlier in the talk. So essentially what the hardware description language is just saying, okay, for these particular values of the weights, here's the lookup table, and we just program that logic element to form that particular lookup table. So just to give you an example of this in detail, let's say I've got a node that just has two inputs that are coming from two nodes from within the network. I have some weight W13, W12 that's multiplying x1 and x2, and then I need to find this Boolean function, f3, that I should be applying given those particular weights. So this would just be a two-input node. It has an output x3. So I give an example that if I were to do a random draw for these weights, let's say W13 was equal to 0.2, W23 is equal to minus 0.3. If I now go through all possible Boolean values for x1 and x2, then I have this table here where I look at the case first where x1 and x2 is 0. When I multiply by those weights, then I see that the output should be 0. And then so on and so forth for all four possible Boolean values for the inputs. So now this is what's called a truth table or a lookup table, and we can now instantiate that on a FPGA by just using multiplexers that take as input the values of the x's, the different values of x3, and then as x1 and x2 come into here, then this collection of multiplexers then properly produces the output. Now, we actually don't create all these multiplexers. The hardware description language knows how to just take this truth table or lookup table and program that into one of these logic elements. But we're just showing conceptually how this works. And this works quite well up to about 10 inputs. Once you get to more than 10 inputs, then you have an exponential growth on the complexity of one of these nodes. So you really can't make arbitrarily connected inputs. And so that comes into the detail that we have for our output layer. Normally we might have 100 or 200 nodes in a network, and so we can't form the output layer using this trick. And so that's why we use standard adders and multipliers for the output layer, as I mentioned earlier. So now I'd like to go on and show our results for trying to forecast the chaotic dynamics of the Mackey-Glass equations. And so instead of taking some real physical signal in the world that goes through a sensor and then goes into an analog to digital converter, we just use a standard computer to integrate the Mackey-Glass delay differential equations. These are very well known in the field of nonlinear dynamics. I'm using the symbol R to represent the Mackey-Glass variable. And I have this differential equation that has a decay rate alpha, and then it has this highly nonlinear function that is driving R. And so for these particular values of the parameters, the Mackey-Glass equations, it displays chaos. This figure shows the time delay embedding of the trajectory of the Mackey-Glass system. It's a very pretty strange attractor, and the idea is that I'm going to integrate for some period of time the Mackey-Glass equations. Then that is sampled at discrete times. We then binarize each one of those real values using an 8-bit representation, and then I take that loaded onto the Field Programmable Gate Array, and the variable R now is the input U to the reservoir computer. We then use that signal to drive the reservoir. We then discretely sample data that is the state of the reservoir at the same time step that we're feeding data in. We record that block of data, transfer it to a computer, do offline training of the weights, and we take those weights and then put them back back to the reservoir. So just to give a little bit of experimental details, as I've already mentioned, we can do a prediction every 6 nanoseconds or so. That is a prediction rate of 160 megahertz. The reservoir that we use for the data I'm about to show you has 100 nodes. We have an average in degree of 2 and a spectral radius of about 1.5. And the mean delay time along the links is 11 nanoseconds. We connect all 8 bits. All 8 bits go together to a node within the network, and we connect it to half of the reservoir nodes. And this mean link time delay, we've adjusted to improve the performance. And the Mackey-Glass equations are discretely sampled every 5 time units of Mackey-Glass. So remember, Mackey-Glass is just a mathematical expression. The time has no units in it. But on the physical device of our reservoir computer, 5 temporal units of Mackey-Glass corresponds to 6.25 nanoseconds. The Lyapunov time for the Mackey-Glass with those parameters, which is the inverse of the largest Lyapunov exponent, is 116 of these dimensionless time units, and that corresponds to 145 nanoseconds in real time on the FPGA. We train with 1,500 samples, which corresponds to 7,500 time units, or a little bit less than 10 microseconds. And so we went and did this training, we put the weights back on the chip, and then we played back the same training data set to see how well it performs. So the first part of this graph, we're showing the Mackey-Glass variable. I'm sorry, I forgot the label on that, so that's R as a function of real time. The data up until the dashed line is when we're just playing back the training set to the trained reservoir computer. And you can see that the agreement is pretty good. I mean, there are some places where it's struggling a little bit. But then after the dashed line, we rapidly switch the input, so we're no longer feeding training data into it. We take the output of the reservoir and then feed it back to the input. So from the dashed line onward we're now in prediction phase for the Mackey-Glass, and you can see that it does a quite good job of predicting the dynamics out to quite a long time. If we look out at 1 Lyapunov time, which is 145 nanoseconds or 0.145 microseconds, the normalized root mean square error is comparable to pretty much the state of the art of any other hardware reservoirs that we know about. And it still looks quite good for times much later. You can see that the errors are starting to build up, but it's roughly getting things right. So to quantify this roughly right, what I'd like to show is the attractor that is created by this autonomous forecasting machine. So on the top left is the actual attractor that has got the same discrete sampling time and the same 8-bit representation. And so that's as good as you can get. That's our ground truth. The middle plot shows the attractor that's forecasted by our FPGA device. It certainly looks a little bit messier, but it basically gets quite a bit of the structure correct. If we look at the power spectrum of the actual and the forecasted, it's pretty close. The main peak is slightly off in frequency, but some of the other major peaks in the power spectrum are roughly there if you squint your eyes a little bit. And then I'd like to say that the reservoir doesn't always work. Once in a while, you get a reservoir that doesn't perform as well. If you recall some of those plots that I showed earlier from Aaron Griffin, where he showed this distribution of if you randomly choose a network, you get some that perform better than others. And this down the bottom left shows the attractor for a case where the reservoir is just not able to forecast. It does a great job during the training phase. It has very, very low error in the training phase, but then when you close the switch, it fails to forecast the attractor. So this looks nothing at all like the original Mackey-Glass system, and the power spectrum is just completely wrong. The idea that the community is starting to develop is that this failure happens when you don't have the fading memory requirement that people have for a reservoir computer. And this means that the input signal just never was able to entrain the dynamics of the network. Now, just to show you some how we adjusted parameters in the experiment, this here is a plot of the root mean square error of the performance of the forecasting task, that is over a Lyapunov exponent time after we started forecasting. We'll look at what the error rate is like. And this here, we adjusted the mean link delay time, and we see that there is an optimum, but then it's pretty insensitive. Once you get to that optimum value at a delay time, and sorry, I left out the physical units, this is in nanoseconds. Once you roughly get to 9 or 10 nanoseconds, then it's pretty flat, and there's no need to increase the delay further. But this does show that it's important to match the time scale of the fading memory to the time scale of the signal that's coming in that you're trying to forecast. If we then look at the performance on the spectral radius of the matrix, the connectivity matrix for the internal connections within the reservoir itself, the spectral radius is just the maximum absolute value of the eigenvalues of that connectivity matrix, and it's believed that it's important to keep that at around 1. And what we see here is that there really isn't that much dependence on the spectral radius. It certainly is a little bit better when you're at 1, but it just really doesn't strongly depend on the spectral radius. In fact, some of the experiments we performed was quite a bit higher than 1. And then if we look at what happens when we change the in degree for each of the nodes, that is the in degree from connections from other nodes within the network, we find that there's a little bit better performance when the in degree somewhere around 2 or 3, but again, there's not very strong dependence on the in degree. Now I'd like to go on to the final topic, really changing gears here to talk about how we can control dynamical systems using reservoir computers. And just to remind you about how we go about controlling dynamical systems, the idea is that I have this box over here that's called dynamical system, a system, or a plant, or a process. The idea is that I've got something that I can measure about that plant using some kind of sensor. I then take that output and compare that to some desired or reference behavior. That gives me an error between what I want it to be and what it's actually doing. I then have some black box, it's called a controller, that then generates signals that can be applied to some adjustable system parameter, some knob that I can change that will adjust the dynamics of the system. And so this is called a closed loop feedback system for trying to control the dynamics of the plant. So in a little bit more mathematical detail, the plant has some dynamics y that we're assuming is described by some kind of differential equations that depends on the current state of the plant, as well as some inputs to some accessible variable or knob, and that the dynamics of u of t is going to be some function g of both the desired behavior and the current state of the system. G is what, as a control engineer, I need to design in order to control the plant effectively. And the goal is that I would like the plant to do what I'm asking it to. So in the long time limit, I'd like the desired behavior, R of t, to be equal to the plant dynamics. And so one way to go about making a nonlinear controller is to somehow figure out how to invert this function f. That is, I want to invert the dynamics of the plant. And in many cases, when f is complicated, let's say it might be a chaotic system, it may not be possible to invert the dynamics of the plant. And even finding an approximate inversion is very could be mathematically challenging or even impossible. So our idea is to use a reservoir computer and give it this task of essentially inverting the plant dynamics, figuring out how I generate this function g so that the reservoir computer outputs signals that are controlling the plant and forcing the output to be equal to the input. And a lot of the work that we're doing is based on this paper from 2012 that essentially sets out most of the basic components that we use here. But what we find is that if we try to apply exactly the technique that was described in that paper, we don't find very good control of complicated systems such as chaotic dynamics. And so what we realized is that we could take a small reservoir computer to attempt to control the plant. If I don't have very many nodes in that reservoir, it doesn't do a very good job of inverting the plant or controlling it, but it sort of does an okay job. But now I can think of the first reservoir computer and plant now as a larger dynamical system, and now I can add a layer, add another reservoir computer that's now trying to control the plant plus the first reservoir computer. So the idea is that I can make a layered structure of adding more and more reservoir computers to get hopefully better and better control of the plant. So I can think of this as layers of an onion, or perhaps a little bit more poetic Russian dolls that are all nested one inside the other. And what we find is that if I just try to take one controller, one reservoir computer as a controller, and just increase the number of nodes, I do get better and better, but then it really doesn't improve much beyond that. And it's fairly costly to increase the number of nodes in one of these reservoirs, in that the time it takes me to do this least square evaluation scales in roughly the cube of the number of nodes within a reservoir. Whereas if I just have a small reservoir and then add another and add another, it turns out that the cost of adding layers only scales with the number of nodes in each one of them. So we keep the number of nodes small in each reservoir, but then add many layers. And that ends up being much more computationally efficient. And for some numerical simulations that we did, where we were trying to control the dynamics of the Lorentz chaotic system, what I'm showing here are plots as we add each layer of the reservoir. So when we add the first layer, we see that the error between the desired state and the actual state decreases quite quickly, but then it just kind of flattens out. We don't get any better. if we then add another layer, train it, and then apply it, beyond this dashed line shows after we apply the trained second layer, and we see that the error decreases again, and another layer decreases, decreases, decreases. And please note that this is a logarithmic scale here. So adding layers seems to help, and but if I have more nodes per layer, it actually hurts a little bit. So there's an optimum size, and we find that's about 30 nodes, and that seems pretty independent of the size of the network. Now, we want to apply this to a chaotic electronic circuit. This is just made of discrete electronic components, no field programmable gate arrays involved. What we have is a negative resistor that drives a capacitor that then is coupled to a tank circuit that is an inductor, capacitor, resistor circuit through a nonlinear set of diodes. And this gives rise to kind of a double scroll behavior. Here I'm showing a plot of the voltage across the first capacitor versus the voltage across the second capacitor, and we see a characteristic strange attractor for the system. And the characteristic frequency of the system is quite high. We definitely have frequencies that extend well beyond 100 kilohertz. So this means that if we're going to try to control this dynamical system, we need a reservoir computer that can read an input and then generate a control signal on kind of the inverse of this time scale. So ideally somewhere on the few microsecond time scale. So to try to do control of this system, we want to measure these voltages V1, V2, sent them both to analog to digital converters, and then we instantiated a reservoir computer on a field programmable gate array that then generated the feedback signal, which was then a current that we injected into the capacitor C1 in order to control its dynamics. So again, we've got the plant. In this case, it's this chaotic electronic circuit. We have some vector Y that tells me the state of the system, these two voltages and the current. I'm going to feed those into a set of layered reservoir computers. We go and combine those signals and then feed back a current into the circuit that should control its dynamics. Now, in this case, we've taken a big departure from what I've talked about earlier in this presentation, and that we're using the field programmable gate array, in this case, as a special purpose computer to generate the signal. So essentially, we're just doing a software simulation of a reservoir computer, and we're just using the field programmable gate array as a special purpose computer to accelerate the software. So it turns out that you can highly parallelize the evaluation of the software. And if we were to just use a standard, let's say a C program that just runs in serial, there's no way that we could generate a control signal fast enough, even using a very high-end microcontroller. But we're able to use a very inexpensive field programmable gate array to highly parallelize the code, and we're able to achieve a very low control loop latency. That is, the time from measurement to applying a perturbation is quite fast. It's on the order of about 2 microseconds. So in this first example here, what I'm showing is what happens when we try to control the unstable steady state. It's right when both voltages and the current is equal to 0. So this is perhaps familiar from the controlling chaos literature from a few decades ago, where we tried to take an unstable state and stabilize it using controlled loop feedback. So the first part shows what happens before we turn on the controller. We've already collected the data, we've trained the reservoir computer inside the dash line, so we turn the switch and we control the system. And so we see a very quick, just within tens of microseconds, collapse the dynamics down onto something that's very close to the desired state. So the bottom plot shows the current that we're injecting into the system. The currents are only on the order of 20 to 40 microamps, whereas the typical current that's flowing through the inductor in the circuit is more on the order of a milliamp. So we're really putting in relatively small perturbations to the system. So then we see that those perturbations start off quite large, there's some oscillations, and then it's oscillating just down around the kind of 5 to 10 microamp level. We then turn on the second layer, second reservoir computer, and it results in a little bit bigger perturbations. It seems like the second layer wasn't helping quite as much, but in the plots I'll show you, those are at pretty high frequency, and we tend to do a good job of keeping it pretty stabilized around the fixed point that we're trying to stabilize. Here I'm showing a plot again of the voltage V1 versus V2. We're just showing this as a plot of the points that we collected. We're not connecting any of the points, but you can still see kind of the similar attractor structure that I showed a couple of slides ago. And so the blue points show the uncontrolled attractor, and then we're trying to stabilize the fixed point. That's right where V1 and V2 are equal to 0. And it turns out that this is a pretty difficult fixed point to stabilize. It's an unstable saddle that's in the center of the attractor. And if you only measure V1 and V2, you can control this with standard linear control techniques, but it's pretty finicky. There's only a tiny window where you really can effectively control the system. Now, in this blow-up, the red dot represents the target state where both voltages are equal to 0. The first controller does a pretty good job. Those are the yellow or cold points, but you see it shifted quite a bit over to one side, so that there's a little bit of offset. When we add the second controller, then we do a better job of really keeping it around the fixed point, but you can see that it still has some noise about that. And that's mainly due to the intrinsic noise in the measurement process. And you can see that these points are only showing up in discrete values, and that's because the analog digital converter was only giving us a certain number of bits resolution of the system. Here's another case where there are two other fixed points that are in the center of each one of the leaves of the attractor. And so what our goal is to first stabilize it to one of those fixed points, and then we wanted to guide the system to go over to one of the other fixed points. So what we have here is just time series data showing that going on. We have just the chaotic dynamics at the first dash line. We turn on the first controller. We end up bringing it to one of the fixed points, and then we paint it over to the next one and then bring it back. So we're sweeping it back and forth in a controlled fashion between the two fixed points. And the bottom curve shows the control signal that we apply. So when we're on one of the fixed points, the control signal is relatively small, but when we're doing the painting, that's not a dynamical state of the system trying to pass through to get to the other one. So we have to give relatively large control perturbations to the system to get it to go from one to the other. And then when we add the second controller, then we see that the perturbations that we have to apply in doing this guiding or painting process is a little bit larger. Excuse me, a little bit smaller. And this just shows the attractor. The two fixed points are at the center of each one of the leaves of the attractor. The red dots show the desired behavior of taking it from one of the fixed points and then painting it over to the other one and then bringing it back. So we're just going back and forth between there. And the green and the gold points show the actual trajectory. So it's sitting somewhere over here, and it doesn't quite follow the desired behavior. The control isn't perfect, but again, this is taking it on the path that is not a natural behavior of the attractor, and you really need a full nonlinear controller to be able to try to affect this process. Adding the second controller, that's the dots and greens, we tend to get a tighter cluster of points around each one of the fixed points, but the error when we're passing it from one to the other seems to be about the same. Now here's a third example of where instead of trying to control the system to a steady state, we're trying to send it to a periodic state, something that's close to one of the leaves on the attractor, but it's definitely not a state that is inherently part of the attractor. So the same kind of plot over here to the on this side shows the uncontrolled dynamics. There's no control error. Then at the dash line, we turn on the controller and we see that it's going into some periodic state. And since this is not a natural state of the attractor, we have to constantly apply relatively large control signals to the system to keep it stabilized there. When we add the second controller, we see that the control perturbations decrease somewhat. And this shows the attractor. The blue points are the uncontrolled attractor. The red shows some elliptical orbit that we tried to force it to. So again, it's somewhere close to the attractor, but it's definitely not a orbit that is natural to this attractor. The gold dots show what happens with the first layer. We see that there's a little bit of error there. The green dots show what happens when we add the second layer. We see that the control improves a little bit. It's not perfect, but it's pretty good. So in summary for this presentation, I've tried to show you that field programmable gate arrays are a very promising experimental substrate for studying complex autonomous Boolean networks. I showed you an example of how we could make spiking-like neuronal networks. So if someone is interested in making a spiky-like information processor, you can use collections of logic gates to make neurons, and you can connect them into complex networks. I then spent most of the talk on discussing how you make reservoir computers on these field programmable gate arrays. I have stressed before that it's very easy to integrate these field programmable gate arrays with the existing computer infrastructure. There's a whole industry set up of how we transfer data at very high speed between a field programmable gate array and an on-chip computer. I've then shown you the application doing high-speed forecasting using a reservoir computer for forecasting a chaotic dynamical system, and that this works at very high speed. So we believe that our forecasting rate is still about the highest that anyone has ever obtained in an experimental system. And then finally, I told you about using a reservoir computer as a universal controller for dynamical systems. In this case, the reservoir computer was just done by software simulations, but we used a field programmable gate array to do everything in parallel so that we could have very high-speed control. Thank you for your time.